Can you hear me? Yes.
I can hear you. You're breaking up a little, but
Yeah, you can start right now.
okay. Welcome, everyone. It's a pleasure to be here today to talk about the history of the AASHTO LRFD bridge design specifications, including the development of live load model, the live load model, and load factors. That's kind of a long title for a presentation. Really, it's in the past I've taught a class similar to your class in bridge engineering, and this grew out of one of my lectures, one of my first lectures, to introduce students to the actual specification and but how understanding where it came from and where it might go is important to understand when you're using the actual document. In this presentation, I'll be using the word specification and code. I try to use the word specification. That's an AASHTO term. When it comes to codes, that's pretty much the building code or the ACI 318 building code. In AASHTO speak, we call a specification the code. So, see, I might use the word code, but but reality is when I say the word specification, throw the word code in there as well. A little bit about myself. I am a practicing bridge engineer. I'm the chief bridge engineer of CHA Consulting. We are about a 1,600 person firm, East Coast firm. Our headquarters are in Albany, New York. We go as far south as Florida, Miami, as far west as Indianapolis. So we pretty much an East Coast company with 1,600 employees. We have about 85 bridge engineers on staff. So my job as the chief bridge engineer is I'm a technical resource to all 85 bridge engineers. I'm here as a to answer questions, to solve problems, to do training like we're talking today. As a matter of fact, this presentation you're getting today, I actually presented to our staff a couple months ago. So it's a good presentation. It's one of my favorite ones that I put together to talk about the history of the LRFD code or specification. I reside in Rocky Hill, Connecticut, just south of Hartford, Connecticut, which is why I'm not there in person today. Any of you who have driven through New York City this time of day realize why I'm doing this virtually, because to get from between here and there is not an easy task, even on a good day. So I apologize for not being there in person. So let's get into it. Hold on one second. I got to advance my slide. There we go. So we're going to talk a lot about the history of the bridge specifications in the United States. The AASHTO's LRFD bridge design specifications are actually used around the world. Last time I checked, there were about 80 countries using the AASHTO LRFD. Europeans have their own code. There's a European Union code out there. Canada has their own code. Scandinavia has their own code. Japan, Germany, but a lot of other countries do use the AASHTO. But we're going to talk really about the United States and the specifications here. I feel it's important to teach this history to you students because it has been an evolutionary process, and to understand where the code came from and what it actually means will help you in using the code or the specification in designing bridges and as you move forward in your career. So a little bit of history. We're going to turn back the clocks quite a bit before my time. Like I said, I've been practicing engineering since 1983, but this goes way back pre-1900s. In the 1800s, the early bridges were built by what they called master builders. These were people who invented structures, like in the photo was a Howe truss. The person who invented the Howe truss is a guy named William Howe. He patented his design. So if you wanted to build a Howe truss, you would contact William Howe and he would design you a bridge. But there were no specifications. They were basically built by seat of the pants. Um, I'm sure some calculations were run, but there was no specification or code to design against. Covered bridges were very popular in 1800s. Interesting tidbit, a little fact. People ask, why are covered bridges covered? And people think, oh, it's so the horses don't get wet when it's raining, or people can hide in the bridge during a rainstorm. Well, I guess partially that is true. But the real reason why covered bridges are covered is because wood rots. So the idea of the covering, the siding and the roof is to keep water off the truss, to keep the truss from deteriorating. So it's a fact that a lot of people don't realize why we cover bridges. So a little side note there. There were many patented designs. If you study structural engineering, you'll read about the Pratt truss, the Howe truss. There's different names, and these are the name of the people who invented these trusses. And what they did in those days, they actually not only invented the truss, then they would patent it and sell the truss. So again, if you were like a railroad or a highway department or road department, you would hire somebody like William Howe to design and build you a truss. 1870s come along. A big thing in the 1870s were railroads. They were really significant. Still not a lot of highways in the 1870s, but there were lots of railroads around the U.S. And at that time, 1 out of 4 bridges were failing. And this graphic shown on the right is showing the failure of a bridge from 1876. At that time, though, in the 1870s, the failure rate was 40 bridges per year were collapsing. So you think about that. They were having a bridge collapse almost every week, probably every other week. If you had that kind of failure rate right now in the United States, it would be a national crisis. If we have one bridge collapse a year, that's a big deal. Usually it's one every 10 years, but at that time, one every 40 per year, every week and a half or so. So the public was losing confidence in the engineers. So in December 1876, a good example is a railroad bridge failed with a passenger train going over it, and 80 people died. And that was kind of the last straw. It was a Howe truss, as we showed in the previous photo, that collapsed. It was designed by, as I said before, seat of the pants engineering. And when it was originally built, it was tested with 6 locomotives, and it survived that test. But over time, it'd probably been in service for 20, 30 years or so, and some of that rot may have taken place, and the bridge failed. So essentially, the bridge had a factor of safety of 1.0, that even a minor amount of rot or corrosion caused the bridge to collapse. So the American Society of Civil Engineers met, and yes, they did exist at that time. And the quote from their investigation of the collapse was that the construction of the truss violated every canon of our standard of practice. So they, in the 1870s, they decided they needed to do something. We needed a national code or specification for designing bridges. So 1894 is a very momentous date in the world of bridge engineering. A man by the name of Theodore Cooper developed a loading for trains, and that's shown here on the slide. And it consisted of a series of concentrated axle loads that represented locomotives. And I put the graphic underneath the loads, and you can see it's essentially a steam locomotive with a coal car off the back, and actually it's 2 locomotives with 2 coal cars, followed by a series of cars. And the axle loads range from 80,000 pounds for locomotives, 52,000 pounds for the coal car, and then for the following train railroad cars behind the locomotives, it was 8,000 pounds per linear foot. So this was developed by Theodore Cooper, and it became known as the Cooper loading. And there's 2 different loadings. There's E60, where those maximum axle loads are 60,000 pounds, and then there's E80, which essentially is, if I do my math right, 33% higher, which is 80 kips per axle. Interesting thing about the Cooper loading, it is still in use today. We still design bridges for Cooper loading, even though I haven't seen a steam locomotive in my lifetime. But the railroad industry has found out this is a good loading, even for modern locomotives and modern diesel and electric locomotives. This load works well. So it's still in use today. It became a standard, however, over 120 years ago in 1903. December 12th, 1914 is a momentous date. It's the formation of ASHO. I made a note there. There's no T at this time. It's the American Association of State Highway Officials. The T comes in later. At that time, they formed a committee on bridges and allied structures, which is the beginning of the development of a bridge code or specification in the United States. So they were charged with development of specification for highway bridges, for design, for materials that are commonly used for construction. They didn't publish a book per se. They had early specifications were copied. Not sure exactly how they copied them because Xerox machines didn't exist, but they made copies and distributed them to the state DOTs to start designing and building highway bridges in the U.S. And remember, 1914, if you think about what the world looked like in 1914, cars were literally just invented about 10 years before. And so we're not talking a lot of trucks. We're talking small cars and small trucks, but nothing significant. 1931 was a momentous day in the history of bridges. ASHO at that time published the first actual specification in print format, and it was entitled The Standard Specifications for Highway Bridges and Incidental Structures. This document stayed in existence until the early 2000s, so think about that, a specification that was used for over 70 years. It's based on the working stress method, and the working stress method is we don't use factored loads. All load factors are 1.0. So instead of designing for an ultimate strength, we design for a working stress or an allowable stress. A good example in working stress for structural steel design, we calculate the bending stresses in beams with unfactored loads, and we assign an allowable stress to the steel, typically 0.55 times the yield stress of the steel. So that was in use for many years. When I first started my career in the 1980s, we were still using working stress method. It is an easy method to design to. Without having load factors, it's pretty simple. But as anything, the codes get more sophisticated and more complicated as time goes by. In 1931, they developed a truck loading that was similar to the Cooper loading, with axles representing a truck and then a uniform load representing lines of vehicles on the bridge as well. That loading at that time was called an H loading. H stands for highway loading. And the key thing is in all the loadings we're going to talk about today, including the Cooper loading, is a notional load. And what notional means, it's not a real truck per se. It's a load, and axle loads and axle spacings that do as good a job as we can do to have it mimic the typical trucks that are driving down the roads today or any day. So the key thing is it represents many different loads, not just one particular truck, but it represents multiple types of trucks. And we'll talk quite a bit about that in the upcoming slides. You can adjust it for the overall magnitude if you want to make a bridge, say, safer. Like the Cooper loading, we had the E60 and E80. Similar things could be done with this truck. Again, this is 1931, where large trucks were just really coming into existence, primarily because before 1931, most heavy freight was being hauled on railroads. Highways were very unsophisticated. As a matter of fact, in 1931, most roads were dirt roads, and there was not an interstate highway system like we have today. So the reality was there was no need to design bridges for massive, large trucks because trucks really just didn't exist very much in the 1930s. So 1944 is a very momentous date in the world of bridge engineering. In 1944, AASHTO developed the HS truck, which is the highway semi-truck, which is the modern semi-trailer you see on a highway today. And it was entitled the HS20-44. HS20 was a designation of the vehicle. The 44 designates that it was established in 1944. Truck loading has always been controversial. It continues to be controversial. Trucking companies want to raise the design vehicle load to make so they can drive heavier trucks on highways. The states are fighting that in most cases. But I got these minutes. I actually was given a copy. I've got all the minutes of the AASHTO meetings dating back to the 1920s. And I went in, I have the CD with tons of documents in it. And I looked up, I said, well, if I was going to look at a date, I'm going to go in the Wayback Machine, or I go in the DeLorean, go back in time, where would I go? I'd probably go to 1944 to see how did they develop this HS20 vehicle. So in the review of those minutes, I found the minutes from the 1944 AASHTO committee meeting, or AASHTO committee meeting, and I'll read this to you. It's very funny. So these are the actual minutes from the meeting. The meeting adjourned for lunch at 12:30 p.m. and reconvened at 2:15 p.m. to hear the progress report on the truck loading study being conducted at Texas A&M College. Now it's Texas A&M University. This paper disclosed the results of a tremendous amount of study which had been made on the stress-producing effects of trucks weighed in 47 states at their load meter stations, and offered formulas involving span lengths, length of wheelbase of truck, and total weight of truck, which can be used to investigate these effects. Mr. Culmo, Mr. Wendell, and Mr. Paxton led the discussions that followed, and it soon developed into a free-for-all for them for over them good old fighting words, what design loading should be used. So these people in this meeting were literally almost breaking out in fistfights over what kind of truck we should be designing for. So the chair called for a recess. And then after the meeting got down to normalcy again, everyone calmed down. Mr. Paxton presented a balanced design subcommittee report, which started another argument. They started fighting again. So at the end of the meeting minutes, he writes, as this was about all the refereeing that the chairman could endure in one afternoon, the meeting was adjourned at 5 p.m. So this kind of shows you that truck loading is a fairly, there's a lot of debate in the industry on what we should be designing bridges for. And we're going to talk about how the truck loading changed in the late 1990s, and it was controversial at that time as well. So truck loading has always been controversial. It always will be controversial. And like I said before, the trucking industry continually tries to petition AASHTO to increase the weight of trucks so they can put more freight on their typical semi-trailers. Fortunately, most states are fighting back and saying no, because if we increase the weight of trucks, we have to redesign and rebuild all our bridges, and nobody has a desire or the money to do that. Moving forward, 1963, another momentous date. AASHTO now becomes AASHTO. We added a T, and it's now the American Association of State Highway and Transportation Officials, which is interesting because the bridge code, the bridge specification, you might say adding the word transportation means it's not just highways, that maybe this includes railroads. No, the AASHTO bridge specifications shown here in the graphic only did highway bridges. Railroad was done by another group called AREMA, which is now used to be called AREA. So there is a separate railroad code out there. But anyway, AASHTO now covers both highway and other types of transportation, like ports and airports and shipping ports and things like that. So this, at the time, AASHTO covered all transportation structures with the exception of railroads. They continued to publish the standard specifications for highway bridges. Remember, that started back in the 30s. They did start updating this document as time went by. In the 1970s, they added load factor design, which is a precursor to LRFD. And it went through a number of different editions, and the last edition was the 17th edition, published in 2002 at that time. And we're going to talk at that. It was an interesting era, the early 2000s, because we actually ended up with two specifications at that time. So we'll talk about how that happened. But a little bit about what is AASHTO. You should understand what AASHTO is and how AASHTO functions to know how the code changes and how how does this document actually get published. So this is a quote from AASHTO's website. They're a nonprofit, nonpartisan association representing highway and transportation departments. So the key word is departments. Primarily what AASHTO is the 50 DOTs, plus the District of Columbia and Puerto Rico. So pretty much what AASHTO is every state in the country is a member of AASHTO. People like me, being a consultant, or people like you, being a student, you cannot be a member of AASHTO. AASHTO, you have to work for a DOT to be a member of AASHTO. And essentially, the AASHTO Bridge Committee has 52 voting members. Again, one for each state, plus one vote for the District of Columbia and one for Puerto Rico. So this photograph shown below is a photo from one of their annual meetings a few years ago. You'll notice there's more than 52 people there. States are allowed to have up to 3 people participate in the annual meetings. So we probably have about 100 people in that photo. But again, all 50 states are represented, and all 50 states plus DC and Puerto Rico have an equal vote. So it's kind of like the best way to compare AASHTO is to the US Senate, where every state has equal representation. It's not based on population or number of bridges or whatever. AASHTO is an organization that has equal representation from every state in the country. The diagram on the right I got that from the AASHTO website. This is the overall AASHTO organization. And you can see there's a number of different committees and forums and things like that. But the lower left are the technical committees that are out there. You can see Bridges and Structures is one of those technical committees. There's a committee on design, which is really highway design, traffic engineering, construction, maintenance, and you can see the rest. So these are the technical committees. But I can tell you, very straight-faced, the Bridges and Structures Committee is by far the most active committee at AASHTO. They publish about 30 documents they maintain. Significant effort this group puts in every year. And you compare it to the Committee on Construction, they have 1 document. The AASHTO Bridge Committee has got 30 documents, including the LRFD specifications that we're here to talk about today. So very active committee. These people shown in the photo work very hard to manage and maintain the AASHTO Bridge specifications. So a little bit about the structure of the Committee on Bridges and Structures, which it used to be called the Subcommittee on Bridges and Structures. It was SCOBS, SCOBS. A couple of years ago, they changed it to just the Committee on Bridges and Structure, COBS or CBS. For about 5 years now, they've been using both acronyms. For the most part, we're settling in on COBS, COBS, Committee on Bridges and Structures. Within that committee, they have 20 technical committees, and these are the committees that do the bulk of the work for AASHTO as far as maintaining the specifications. And you can see these committees cover just about every subject in bridge engineering. And each one of these committees is responsible for the description shown. The biggest committees in the overall committee on bridges and structure is T10, the concrete bridge committee, and T14, the structural steel committee. The seismic committee, T3, is very active. Right now, the bridge preservation committee is very active. There's a lot going on with that. But as you can see, they cover all aspects of bridge engineering. And again, each committee is assigned to manage a certain portion of the AASHTO LRFC bridge specifications. I put a note on the bottom. This will change in the next few years. Our company, myself, I was hired to look at their committee structure and make recommendations to improve their committee structure. And there will be a change. The 20 committees will probably reduce down to 13 committees. And we're combining a few committees to make them more efficient. So that'll probably come out probably next summer. That'll be a change. But for now, this is what you need to know. So what does the committee, what do these committees do? These technical committees, they all meet at least once a year. But many of the committees do meet more than once. Like, for instance, the Concrete and Steel Committee, Construction Committee all meet multiple times a year. I think concrete meets 4 times a year. Steel meets at least 3. Construction Committee, I know, meets 2. So these are very hardworking people, and they do the body of the work for changes in the code and the specification. A little bit about names. We're going to talk a lot today about specific text and names and what they mean. And there are 3 types of documents published by the AASHTO Bridge Committee. First is a specification, which is a document written in specification language format that is intended to be adopted in whole as part of a design process. That's an actual definition of what a specification is. In reality, a specification is mandatory. You have to follow a specification. It is not up for debate. Although a DOT can override a specification, they can choose to say, well, we're not going to follow this provision, we're going to follow a different provision. But by and large, bridge engineers who are practicing, if you're using a specification, you have to follow what's in the specification. The only time you vary from that is if a DOT says we waive this provision, or here's an alternate provision for a certain thing. And that does happen. The next thing is a guide specification, which is a document written in the same format that may be adopted, and I underline may, in whole or in part as part of a design specification. So the best way to describe a guide specification is an optional document. It's a document that you can use. You don't have to use it, but an owner might say, I want you to use this guide specification, and this is what you should base your design on. And a good example of that would be, there is a guide specification for design of pedestrian bridges. A lot of states will say, if you're going to design a pedestrian bridge, you design using that guide specification and treat it the same as you would a full specification. The last type is a guideline. A guideline is basically a reference document that can be used to develop designs, but it's not mandatory, and it's something that is optional that you can use at your discretion, or really at the owner's discretion. And when I mention owners, I'm talking about DOTs. DOTs own bridges, not individuals. So a little bit about how specs change, and they do change over time, quite a bit actually. There have been years where up to 250 pages of the AASHTO specification would change on a yearly basis. That's about 10% of the document can be revised in any given year. Actually, what's happening now is they used to revise the document every year. That got too onerous. So now what they do is they revise the document every 3 years. So every 3 years, we expect to see about 300 or 400 pages of changes to the document, which makes it interesting to be a bridge engineer because things are constantly changing. That's just the way things are. But the source of changes, primarily it's through research. The Transportation Research Board, which is TRB, funds research under the National Cooperative Highway Research Program, which is NCHRP. What this is basically, all 50 states pool money into the National Cooperative Highway Research Program, and that program will pick certain research projects that are worthy of study and fund that research and get it completed. And much of that research does end up in changes to the specification or the code. The key word in NCHRP is the C, which is cooperative, which means that all 50 states participate in this research. Some changes come out of university research, sometimes funded by member states. We see a lot of that. Some states do an awful lot of research, and New Jersey does quite a bit of research. Texas does a lot of research. Florida does a lot of research, and often those research projects result in changes to the specification. Occasionally, we have industry doing research. There might be some done by the steel industry or the concrete industry. That does happen from time to time. And then I put on the bottom individual engineers. it's rare, but if I see a mistake in the code, and there's a couple things that I'm considering sending proposed revisions in, I can send a revision into a state DOT, let's say the chief bridge engineer for a DOT, and suggest that a change be made to the specification if I think there's an error or just something that's not clear. And I'll show later some examples of AASHTO provisions that are far from clear, and sometimes editorial stuff is important. So as I mentioned before, the standard specifications for highway bridges was put together in the 1930s, and it was in place till 2002. It was the last revision made to that document. So why did they stop updating the standard specifications? And the answer is, in 1986, AASHTO decided to initiate a study to develop a new specification. The world was going to load and resistance factor design, or LRFD, and the bridge committee felt it was a need to update the bridge code or specification to LRFD. So around the world, countries like Canada had already done this, Scandinavia had already done this, and I think Europe as well. So there was a need, or the understanding was that we were falling behind the rest of the world, so we needed to update the specification. So in 1986, a study was initiated. The key thing with LRFD, it's a probability-based code, and I'll explain what that means in a few slides. The goal being to have uniform reliability of all bridges, to make sure that a steel bridge and a concrete bridge and a timber bridge all have the same reliability or the same probability of failure. That was something that was a goal and the basis of the LRFD code. This code was written by consultants. Majeski Masters out of Pennsylvania was the primary investigator, and they had a host of other people working with them. But they started the work in 1986, and you look at it, they completed it in 1994. So it was 8 years of work. It was a monumental effort to come up with this. So a little bit about, I mentioned before, the LRFD code is a probability-based code. So what does that actually mean? And there are two different levels of probabilistic design. Level 3, and I took this text out of the research paper that was part of that study. Level 3 is a full probabilistic design. I'll let you read that bullet. The key to the full probabilistic design is it requires a ton of data and a lot of work and something that we call Monte Carlo simulations. I'll demonstrate that in the next slide. And then level 2 is a lesser method using first order, second moment method. And you can read the text below. It's statistical characteristics of load and resistance, and you assume that load and resistance are statistically independent, which is a very valid assumption. The key thing is the AASHTO LRFD code was based on level 2 methods. Okay, enough about code methods, but a little bit about Monte Carlo simulations. And the reason, if you're looking at a true probability of probability design approach, when you look at an equation, and this is an equation for a reinforced concrete beam, I should say a beam that's either reinforced, pre-stressed, or a combination of reinforcing and pre-stressing, and actually doubly reinforced, so you got AS prime and AS. Very complicated equation. This is what we designed for. Now, it seems like it's really nasty, but the reality is if your beam is not pre-stressed, the whole first term drops out. If you're singly reinforced, the third term drops out. And really it comes down to the center one is what you probably learned in reinforced concrete design at school. So it looks like a nasty equation, but my point to showing this is every variable in that equation is variable. In other words, the area of steel, A sub S, if I took 1,000 reinforcing bars and measured the area, you'd get a bell curve. They're not all exactly the same area. Same thing with the yield stress. F sub S is the yield stress of the bar. Again, if you took 1,000 samples of rebar and you tested the rebar, you would find there's a bell curve. So every variable in this equation is a bell curve. So that means every variable is variable. Well, Monte Carlo simulations exist. It's a mathematical process where you actually vary each term in the equation based on a defined bell curve. And you have to define the bell curve with data. And then you can run through simulations, usually 10 to 15,000 simulations, and you get a bell curve for the whole equation. And if you take the equation and you look at the mean plus or minus 2 standard deviations, 95% of the data fits under that bell curve. This is the kind of approach you could take. This is a full probabilistic approach. The problem with it is, to develop this, you'd have to do it for every equation in the book. It would take decades to do this work. It's just not feasible. So they take a simpler approach, looking at just load and resistance, really just look at those two variables And so instead of looking at each variable in this reinforced concrete equation, they just look at, okay, we designed this, and here's the actual strength of it. We designed the steel beam, here's the actual strength. And they use that as the basis for their code. Much simpler approach. So the code, this LRFT specification was adopted by AASHTO in 1996. Interestingly enough, I was actually a delegate to AASHTO. I worked for the Connecticut DOT in 1996. I worked in the bridge design unit at Connecticut DOT, and I was a delegate in 1996. I voted in favor of this document, so you can blame me partially, me and 47 other people. Once it was adopted, though, it wasn't initially used. People were still set in their ways. Standard specifications have been around for 70 years, and nobody was just going to drop their pencils and switch the code right away. So there was a definite period of transition where we had two design specifications in use. So a lot of states were experimenting with LRFD. Most were still using the standard specifications at this time. So a little later in the 2000s, around 2002, 2003, the AASHTO committee, as we mentioned before, one of their jobs is to maintain the code. Well, they had to maintain two codes, the standard specifications and the LRFD code. And this is a volunteer organization. They don't get paid for this work. And it was getting too difficult. So they decided in 2002 to archive or sunset the standard specifications for bridges. So that was the 17th edition published in 2002, and nothing has been changed in that document since. So now, time has passed. Now all states are designing an LRFD. The standard specifications are still out there. We occasionally refer back to them if we're looking at an old bridge and trying to figure out how it was designed. But reality is all states are now using LRFD. So now you know the history of the specification, a little bit about the format. You've probably been using it quite a bit already in class, but it's divided up into AASHTO speak as sections. You might call them chapters, but AASHTO calls them sections. There's 15 sections shown on the right. The key thing when you look down this list, unlike the building code, where we have the International Building Code, the ACI 318 Bridge Building Code, and the AISC steel specifications. So if you design a building, you have 3 or maybe 4 different specifications to follow. In bridges, it's an all-inclusive document. It covers concrete, steel, loads, wood structures, aluminum structures, foundations, retaining walls. It covers everything on a bridge. It's covered in one document, which is why the AASHTO LRFD specification is over 2,000 pages long, because it's essentially taking 4 or 5 or even 6 codes and combining them into one document. So most sections in the document have a separate table of contents for each section. So the concrete section will have a table of contents just for concrete. It'll have a definition of the scope. It'll have definitions for words used in that section. And then notation, a very inclusive list showing all the notation used in that particular section or chapter. This is important because really these chapters are somewhat independent. You do have to jump around a little bit in the code, but there's some very significant sections. I forgot to look. I was going to look today. The concrete structures section has something like over 300 pages of text in it. So they're very substantial documents. A little bit on notation. The notation in the beginning of each section includes the units. And for the most part, we use kips and inches for units. And the reason we use kips and inches, you might say, why do we use kips? Why do you use kilopounds, 1,000 pounds, and inches? Why are we doing that? And the answer is, if you do engineering long enough, you realize if you use kips and inches for your units, you get answers like 315 or 6,250 or so. You get numbers that are you can actually grasp. Why not metric? You know, why are we not using metric? Well, we actually did use metric in the early 2000s. The AASHTO LRFD specification, when it was first published, it was published in dual units. There was a U.S. customary units, which some people call English. I don't call it English because if you go to England, they use metric in England. So really, it's a U.S. customary units is what we call English, and then metric. They had a metric edition. So why not metric? Well, in the early 2000s, federal highway, and there was a federal law that said we had to switch over by, I think, about 2005 or 6. We had to switch over to metric. And 49 states switched to metric over a period of about 5 years. Interesting, the 50th state, Rhode Island DOT, never switched over to metric. They just decided they weren't, you know, they weren't going to do it unless somebody took them, you know, tied them up and pulled them along kicking and screaming, but they didn't want to switch over. One of the problems with metric, though, when you do calculations in metric, you got to decide, well, what units are we going to use? And AASHTO decided to go with millimeters and kilonewtons. When you do calculations with millimeters and kilonewtons, you get answers like 6.2 times 10 to the ninth power for a moment. And nobody had a feel for what that even meant and what that even was. So we were continually getting an answer and converting it back to US customer units to see if it made sense. But we did it. We converted to metric. We had the entire country, with the exception of Rhode Island, was designing in metric. Then, right around 2006, Congress changed the law and made metric optional. Now, metric at the time was only required for federal projects, for bridges and federal housing. For private construction, U.S. customer units was fine. So the problem we had was only about a third of the industry switched over to metric, and the rest of the industry was still using feet and inches. So when the Congress decided to make metric optional, within 3 months, 25 states switched back to U.S. customer units, and within about 3 years, all the states switched back to U.S. customer units. So a little political thing going on there, and so we do not design in metric. I know you guys probably take classes and you learn how to do calculations in metric. In the bridge industry, I don't know if it's ever going to go metric. Not in my lifetime. I'll probably be dead before they switch again. But right now, we are not using metric in the U.S. at all. Okay, a little bit about format and specs. You've been in the specs a little bit already in your class, but the key thing is the specification language is on the left column, and the right column is reserved for commentary. So you'll notice the article number in this case, I just picked an article out of the book, is 3.4.1. On the left, on the right, it says C 3.4.1. That's commentary. That was a big change when the AASHTO LRFT came out. In the previous standard specifications, there was no commentary. So they would have an equation, and you just had no idea where that equation came from or how to even use that equation. The LRFT, one of the big advantages of LRFT was extensive commentary on the left side to help you in making use of the equations on the right. I'm sorry, the commentary is on the right side to help you use the equations on the left side. And the commentary lines up with the equation. That's very important. You'll see gaps in the commentary because they really work hard to make the commentary line up with the paragraph on the other side of the page. Okay, let's talk a little bit about the LRFD truck loading development. As I mentioned before, we talked about the history of the Cooper loading, and HS-20 came around in 1944, which is the HS-20-44. If you look in the specification now, the current loading is called HL93. I don't know if you all know that. And anyone have a idea what the 93 means? I can't hear you, but the answer is it was developed in 1993. So during the development of the LRFT code, there was a need to look at updating the vehicle because the vehicle was 70 years old, if I can do my math correct. And they wanted to see maybe it's time to start looking at a different design vehicle. And it had been a long time since the 1944. The key thing is the design vehicle, again, as I mentioned before, is not a real truck. It's a notional load that mimics actual traffic. The reality is the HL93, only one HL93 truck, as far as I know, exists. Federal Highway actually built an HL93 truck, and they have it at their research lab in Virginia. It is a notional truck. It's not a real truck, but it mimics actual traffic. The other problem we have is many states have exclusion vehicles. These are vehicles that are grandfathered in. If you go to like Kentucky, for instance, they have coal trucks that are heavier than HL93, so those and heavier than the HS-20. So there was a concern by the committee that all these exclusion vehicles were out there, and that the truck was rather old, and we needed to look at a new truck. So a study was undertaken. So this is what they looked at. This is a plot showing a comparison of the HS-20 moments. We're looking at bending moments compared to these exclusion vehicles. And the key to look at the bottom, the x-axis is the span length of the bridge. The y-axis is the moment ratio, which is the ratio of the exclusion vehicle bending moment to the HS-20 bending moment. Again, this is before LRFD was finalized. They're looking at the old standard specifications to see if the standard specifications were accurate. And there's several plots here. There's M positive, which is the positive bending moment at 0.4 L for a continuous girder. The next one is the negative bending moment at 0.4 L. The next one is the bending moment at the support. And the last one is the bending moment for simple span bridges. Now, I put a red line where it says 1.0. What does that mean? 1.0 means that the exclusion vehicles are creating the same bending moment as the HS20. And you see, virtually nothing is below that line. So almost everything's above the line, as high as 1.83 maybe. What does that mean? It means that these exclusion vehicles for certain span lengths, in this case around 100 feet, was 80% higher than the HS20. They were shocked when they saw this. They're like, wow, the HS20 is not as accurate as it really should be. So this was for bending moment. They also looked at shear. This is a plot for shear. Similar results. The HS20 was up to 1.73 times larger than the HS20 for certain span lengths. So this was the justification for saying we need a different live load. The HS20 live load was no longer accurate. So what are the next steps? The committee told the consultant working on this work to develop a truck that better mimics actual traffic as far as bending moments and shears. They wanted it to work for simple spans and continuous spans, as those diagrams showed. And they also wanted to make sure for continuous spans they can mimic multiple trucks on either side of a pier, maximizing the negative moment of continuous spans. So that was the charge of Majeski and Masters at that time. So if you look at their report, they came up with the options for the committee. The first option was an HTL 57, which is essentially a mimic of what's in the Ontario Bridge Design Code, which is a 1, 2, 3, 4, 5, 6-axle notional truck. Again, it's not a real truck. It's a truck that gives moments and shears that are consistent with trucks driving down the road. So this is the first option they presented to the committee. Second option was called the family of three different design vehicles. The first one, in the upper left, two 25 kip axles 4 feet apart, actually had been in the code since the 40s. It's a tank. It's an army tank. That's what that's supposed to mimic. The second one is your typical dump truck or concrete truck driving down the road. And the one on the bottom is your heavy semi-trailer with cars and trucks in front of it and behind it. So this was recommended by the researchers as another option. The third one, I can't even find a picture of this because they hated it, was a 15-axle notional truck. It was a truck that was like 120 feet long and had 15 axles. And the idea was it was a fictitious truck that would mimic all the loads that are on the being exerted on bridges around the country. It didn't make the final report, so I don't have a diagram of it. Professor Dennis Mertz from the University of Delaware, who unfortunately has passed away, Dennis told me about this 15-axle truck, and he says the committee just hated it. So they took it out of the final report. Never even made the final cut. So that was another option. So they presented this. They spent about 1.5 to 2 years developing these live load models, and they did a ton of research, ton of calculations, and presented it to the AASHTO Committee on Bridges and Structures. And the AASHTO Committee hated it. They hated all of it. They thought it was overly complicated. They didn't like 3 trucks. They didn't like a 5-axle truck. They didn't, the family of 3. They didn't like the 15-axle truck. They hated it. And talk about a way of being discouraged. You spend 1.5 years doing research, and you come in and they tell you, quote, try to make the HS20 or something similar work better. So they did 1.5 years worth of the work, and they were told go back to the drawing board and start again. So they did, and what they did was they said, well, they came up with this idea. We're going to combine the old standard specification HS20 truck, which is the 3-axle truck with 8 kips, 32 and 32 kips, but we're going to put the live load on top of it. You might say, are we not doubling the load? And the answer is you kind of are doubling the load. But what they found was, well, I'll show in a minute. So the idea was the axle loads would cover short span bridges, and the uniform load would cover long span bridges, and it gave good results. They actually did this, and it gave, you'll see in the next slide, very good results. Let's take a look. So what happened here was, you look at it, we got the data now very close to that unison line, unity line of 1, where for different span lengths, this new live load model of truckload and lane load combined work really well. But what's not in this plot was the actual plot was not at 1.0. It was up around 1.4 or 1.6, I think it was. It was up quite a bit higher because you are doubling the live load on the bridge. You're putting the uniform lane load, plus you're adding more load to the bridge. So the solution was to adjust the load factors. At the standard specifications, the live load factor was 2.2, and the LRFD was reduced to 1.75. So the combination of having uniform load and truckload on top of it, factoring it down from 2.2 to 1.75, yielded the results I show on the screen here, which in the world of bridges is very good. That's very accurate. So the HL93 was born in the 1990s as a replacement for the HS20. So a little bit about how the code is developed. I mentioned before the LRFD code is a probability-based code. And this is the basic AASHTO LRFD basis of design, how the code was actually developed. And let's walk through these charts quickly. The chart on the left, the brown curve, is the load curve. And what that is if we put strain gauges or we put gauges on a bridge and ran millions of trucks across a bridge, and you measure the stresses due to those trucks, you would get a bell curve. Most of the trucks are average weight. Some trucks are light, unloaded. Some trucks are overloaded, and there's illegal trucks out there too. So that's the bell curve on the left. The bell curve on the right is the resistance. If I built 1,000 reinforced concrete beams and tested them to failure, I would get a bell curve. Sometimes the concrete's stronger than we designed for. Sometimes the concrete is not as strong as we designed for. And the same thing with the reinforcing steel. So you have two bell curves. So the question I have on the screen is, where the two bell curves intersect, there's an area under those two curves. So the question is, what does that area represent? Does anybody have an idea what that area means? I'm looking at you all, so feel free to pipe in.
Yeah.
Let's think about it. What's happening in that area? You have the load is higher than the resistance. What does that mean?
Right.
I heard something, but I couldn't hear it. Answer? Oh, somebody's coming forward. Good. So what happens when load exceeds resistance?
The bridge would fail.
That's failure, exactly. That is failure. So that little area under the curve is considered failure. Now, does it mean the bridge is going to collapse? No, it just means something might be overstressed. You might crack a beam. You might yield some steel locally, but that is failure. And the reality is there's a potential for that to happen. The question is, how small should we make that area? And the reality is we can't make it zero. It's just not feasible to design a bridge where this never happens. So the question is, how do you design for this? So what they did in the code was they used a thing called a beta factor, which is a beta is the distance between the load curve and the resistance curve. Different codes around the world, I mentioned before, there's multiple probability codes in the world, use different beta factors. And it comes down to what is an acceptable failure rate. And when I say failure, it's not collapse of a bridge. It's you might get some little localized yielding of steel or maybe a crack in a pre-stressed concrete beam. It's not going to drop the bridge. No one's going to die here. But there is a chance that you get a failure rate. I believe the number is 1 in 20,000, but I could be wrong. But the AASHTO code writers and the AASHTO Committee of Bridges and Structures settled in on a beta of 3.5. That is the basis of how the load factors were developed in the LRFD code. And the key thing is, if you want to spread those two curves apart, how do you do it? Well, load is, you can either change the load, make trucks lighter. Well, that wasn't probably going to happen because the trucking industry is a big lobby. So what can you do? You can improve resistance. And how do you do that? With load factors. You design for higher loads. You over-design the beam to handle the case where the load exceeds the resistance. So this is the basis of the LRFD code. This is the famous LRFD plot of beta factors, and 3.5 is the answer. Now, you don't need to know this when you design a bridge. It's built into the code, but it's good to know how it came about, that there actually is a probability of failure built into the code. Nothing is perfect. There is a potential for load to exceed resistance. Now, before we started the lecture, you might have come in, or some of you were here early, we were talking. And I can honestly say, in my career, which is now 40 years I've been designing bridges, I cannot think of one case where a bridge failed in flexure or shear. Even with this case of this probability of having load exceed resistance, there's so much conservatism built into the code that bridges don't fail in flexure and shear. We follow the code, you trust the code, it works. And the reason I bring this up, because there are certain states right now who are starting to increase load. They're starting to say, we're going to design for 1.2 times the HL93 because we have a lot of heavy trucks on the road. But understand, that load, the HL93 load was, they looked at, I forgot to mention before, when they did that study to come up with the HL93, they looked at like 30 million weigh in motion data points from these weigh stations that are out there across the country. And they literally are covering every vehicle that's on the road is covered by the code. Now, mathematically, I can go and check like a concrete truck, and for a certain span length, I may get a slightly higher bending moment than the HL93, but that's built into the code. That's why we have load factors. The load factor gives us that beta, that gives us that separation to make sure bridges are safe. So there's a load equation right there, the famous LRFD design equation, where it's there's an eta factor in the beginning, which you multiply all loads times eta, and then times the summation of the gamma dead loads times dead loads, and the gamma live loads times live load. And that equates out to phi sub r n. So the gammas are load factors for dead load factors for live load, n is a load modifier for all loads, and phi is a resistance factor. In the world of reinforced concrete, I think we call it a strength reduction factor, and AASHTO it's called a resistance factor. And R sub n is the nominal strength of the member. The eta in the beginning, I don't think I cover it in this lecture, but I'll cover it really quickly here. The eta in the equation covers things like redundancy and things like, I'm trying to think, redundancy and whether a bridge is critical or essential. There's no definition for critical or essential, and there's no definition for redundancy. The committee just said, well, I'll just use 5%. That sounds good. So if you have a non-redundant bridge, we design for 5% more load. If you have a severely redundant bridge, which I've never heard of, you can actually reduce the load by 5%. Anyway, it's kind of a silly thing in the code. The people who wrote the code have told me they put the eta factor in as a placeholder. At some point in the future, somebody's going to do research and come up with a real number which should go in there. For the most part, eta is 1.0 for all designs. Okay, I'll quickly go through the load combinations. And this is a table you'll probably get very familiar with in your class. The first column are a bunch of loads like dead loads, dead load wear and service, things like that. And for dead loads, there's gamma sub p, and there's a separate table with gamma p, which we'll talk about in a minute. But under live load, you'll see for strength 1, which is the primary load combination for designing a beam for strength, live load factor is 1.75. The actual research that was done to calibrate the code showed that 1.6, which is consistent with ACI, actually works. But the AASHTO Bridge Committee, they're very conservative and decided they didn't want bridges to change too much. So they recommended using a load factor of 1.75. So it's important to understand the actual load factor for live load has a little bit of fluff built into it. It's higher than it mathematically should be. So I just want to point that out. The dead loads, a big introduction in the AASHTO LRFD was to have this table with dead load factors, and the concept of minimum and maximum load factors. And the idea being is if I have, say, reinforced concrete, that the concrete may be heavier than I assume. We all assume 150 pounds per cubic foot. It might be 160, it might be 140 or 145. So we have 2 load factors. This confuses everybody for years. It still confuses people. In my opinion, they should get rid of this because it's really, how you apply this is really, it's not consistent, but so I'll just move on. But you do have to check, when you design a bridge, you have to check for maximum dead load factors and minimum. Most people just design for maximum because that's usually controlling. So go quickly through some of the combinations. Strength 1 is the basic load combination for designing a bridge for strength. That's the primary load combination we use. And it says without wind. Doesn't mean without wind, but without a hurricane. So we design for that. Strength 2 covers these exclusion vehicles that owners have, like the coal trucks I mentioned before in Kentucky. Strength 3 is a load combination for the design wind load on a structure. Now, most bridges, wind load is not a big deal, but if you have a suspension bridge, you can imagine wind load's a big deal. You'll notice on the bottom of the screen, for strength 3, which is your wind loading, there's no live load. Live load is 0. You might say, why? When I'm designing for a hurricane, why do I not have live load? And the reality is, the design wind loading is usually 130 to 150 miles an hour. The theory being, if you got 150 mile an hour wind, nobody's going to be driving a semi-trailer across a bridge in a 150 mile an hour hurricane. So we're allowed to neglect live load. We design bridges for wind. Strength 4 is a combination for structures that have very high dead load to live load ratios. That would be like a suspension bridge. And you'll notice, again, there's no live load, but you're designing for full dead load. So that's there. Strength 4 is for normal loading with decent wind. So it's regular trucks, but 80 mile an hour wind. You'll see there the live load factor is reduced to 1.35. Again, the theory being in a very high wind storm, you might not have many trucks on the bridge. So we lower the load factor for live load. You get to earthquake, extreme event 1 and 2. I actually taught a class at one time called Design of Bridges for Extreme Events. And extreme events are defined as events that could during the life of the bridge, could lead to collapse of the structure. Things like earthquakes, things like vehicle collision, ship collision, ice dams hitting bridges are covered by extreme events. And there are 2 major extreme events. One is extreme event 1, which is really seismic, and extreme event 2 are all the other extreme events like floods and collision from vehicles. You'll notice the live load is a gamma EQ, and there's commentary. This is the commentary from the code, and it doesn't tell you much, but it does tell you that you can consider a reduced live load, and the theory being the probability of a bridge fully loaded with trucks at the moment an earthquake strikes is very low. Therefore, they recommend in the commentary you can use 0.5. You can reduce your live load to 0.5. However, there has been recent research that shows trucks on a bridge during an earthquake, and this was at the University of Nevada, Reno, they put trucks actually on a bridge in the lab and on a shake table and shook the bridge and found out the trucks actually act as a tuned mass damper and reduce the seismic forces. So it's actually beneficial to have trucks on a bridge during an earthquake. So therefore, a lot of states are going to gamma EQ of 0.0, meaning there's no live load on the bridge for earthquake analysis. But my answer, if you're designing a bridge in a state, most state bridge manuals will tell you what to use for this value. So that's where you would actually come up with that number. Okay, there are several service limit state checks. There's actually 4. I'll quickly go through these. Service 1 is for normal use of the bridge with 70-mile-per-hour wind. And service 3 is looking at pre-stressed concrete structures for crack control. That is a very popular load factor. The load combination is used for pre-stressed concrete girder design. Service 2 is for slip critical connections and steel structures. We're kind of getting down in the weeds here a little bit. And service 4 is for checking, I love this, only for checking tension and pre-stressed concrete columns with the objective of crack control. I don't know anybody in my life who's ever done a service 4 check, but it's there. So let's talk about application of live load. We talked about where the live load came from. Let's figure out how do we apply that live load to our bridge. And the answer is the most common method used is called line girder analysis. And what that is we take a 3-dimensional bridge and break it down into a 2-dimensional structure. Sometimes people call it a 1-dimensional model. I call it a 2-dimensional model, which is X and Y, but no Z. It's just, we calculate what percentage of load is applied to each beam individually. We don't look at it as a grid or a grillage or a 3-dimensional structure. We try to break a 3-dimensional structure down into a 2D structure. So line girder analysis is very simple. It's easier to design for line girder analysis. You get consistent results. It's easy, it's cheap, it works well, and gives you a safe bridge. So professors come up to me all the time and say, why are you not doing 3D analysis of bridges? We have the technology. We have the software to do 3D analysis of bridges. And I agree, we do. And you can get a better answer. You get a more accurate answer. But the reality is, most DOTs want to have all the girders the same size. And this allows you to widen the bridge in the future. So if all the girders are designed as interior girders, and I can widen the bridge, so our goal is to have all the beams the same size. If you do a 3D analysis of a bridge, the results will give you a different load on each girder, guaranteed. So that means every girder is going to be different. So if we take a 3D analysis and we take the largest beam that comes out of that analysis and we make all the beams the same, we've lost all the usefulness of a 3D analysis. We're essentially designing for the least common denominator. So if that's the case, why even bother doing 3D analysis? That's why we do line girder analysis. It's simple, it's easy, and the reality is all the beams come out the same, so we're happy with the results. But we still do 3D analysis. For curved bridges, heavily skewed bridges, we do 3D analysis, or very complex bridges. We get into very complex, even finite element analysis for that. But for the most part, the code is based on line girder analysis. So we'll get into that now. So the idea of a line girder analysis is we apply a percentage of a truck to each girder, which is called the live load distribution factor. Essentially, it's a number, it's a unitless number, but it's like a 0.35 means 35% of the lane load is applied to that particular girder. So essentially what we're doing is converting a 3D problem into a 2D problem. and the distribution factors in the code were based on three-dimensional finite element analyses of multiple bridges, many bridges, that come up with these empirical equations. So they are quite simple. Compared to the old standard specifications, the distribution factor for standard specifications was beam spacing divided by 5.5. You'll see the equations we have now are a little more complicated than that. So there are separate factors for moment and shear. I'll show those in a minute. And the key thing is, when you go to design a bridge, you calculate the load on each beam. For live load, you put an entire lane on the beam, you get your moments and shears, and then you multiply those moments and shears by the live load distribution factor to get it down to what percentage of those moments and shears are acting on each girder. Here's what these equations look like. A guy by the name of Roy Impson came up with these equations in a research project. We sometimes refer to these as the Impson equations. Roy passed away last year, unfortunately, but he was a good friend of mine. And they did a very good research project looking at finite elements that come up with these equations. Now, I said before, the previous equation was S divided by 5.5. You can see this equation now for two or more lanes loaded. There you go. That's a mouthful. You know, S over 9.5 to the 0.6 power times S over span length to the 0.2 power. Then this term with kg. It got a lot more complicated. And there are a lot of people who don't like these equations. They are adamant these are way too difficult, way too complicated. But the reality is we create spreadsheets and we can generate these things very quickly. But one thing I do recommend, by the way, the upper table is for moment. There's a separate table for shear. And you notice in the beginning of the table that the cross-section applicability is listed here, A, E, K, I, J. And this is like what A and K looks like. So you get your bridge that you're designing. You know, I'm doing a bridge type A. You go to the table and you go to A, and there's our distribution factors for one lane loaded and two or more lanes loaded. But what I do caution you is always check the applicability of these equations. For instance, if the span length is less than 20 or more than 240, technically the equation is not applicable. I actually designed a bridge at one time at 250 feet, and I actually contacted the people who did this work, and they said, well, if you use the equation, it's conservative. You can, but over 240 feet, technically you just do a 3D analysis for those special occasions. Lever rule. The equations I showed before were for interior girders. Let me go back a slide. You'll notice these are for interior girders. And down, you'll see, I'm trying to think if it's actually on here. Yeah, if the number of beams are less than 3, or if you're looking at a fascia beam, an outside beam, use what's called the lever rule. So let's talk about what the lever rule is. And essentially what that is a simple statics calculation where you throw the truck on the outside and the truck is 2 feet from the curb line, shown right here. You put half a wheel load, half an axle load here, half an axle load here. You sum moments about the first interior beam. You assume there's a hinge in the deck at that point, and you go through the equation. So it's 0.5 times 4.3 feet plus 0.5 times 10.25 feet divided by the beam spacing, 9.75 feet, and I come up with 0.744 lanes. Now, in the AASHTO LRFD, what they say is if you only have a single lane loaded, you need to multiply that by 1.2. And why do we do that? And the reason for that is it's confusing. I was confused for years on this thing. I just used it, but I didn't know why as a young engineer. But the reality is that typically for loading, we have multiple lanes loaded to cause the maximum moment on a beam. All the equations in the code are based on 2 trucks side by side. The probability of 2 trucks being side by side at any given time is fairly low. So the equations are somewhat not unconservative, but more liberal. But the probability of a single truck driving up the shoulder, like a snowplow, is pretty darn high. So what we do is we multiply by 1.2 because the probability of this load occurring is much higher than the probability of 2 trucks side by side. So in the AASHTO document, if you're using 1 truck, you use 1.2. Now, back to these equations, I go back a slide, you see that is built into these 2 equations. You don't need to use the 1.2 factor for 1 lane loaded. That distribution factor actually accounts for multiple presence, the 1.2. But if you do a hand calculation, like the lever rule, you should apply the 1.2 multiple presence factor. So the last thing I'm going to do in this presentation, we're getting pretty far along here. I want to go through how to read the specification. You might say, I can read, I read English, I know English, I can read it, but as an engineer, you have to be very careful how you read specifications because words do matter. We mentioned before the word notional. A notional load is not a real load. It's an idealization of a physical phenomenon. And notional. So that's something that when you see notional, you have to understand this, like the HL93 is not a real truck. It's an idealization of what's actually out in the real world. The terms shall, should, and may are really important. Shall denotes a requirement, meaning if something says shall, you have to do it. If something says should, it's a strong preference and you probably will do it. If it says may, technically you have the option. You don't have to use that provision. And I'll give some examples in a minute. State DOT bridge manuals typically define the shoulds and the may. They'll actually say you should. In this particular criteria, may means shall. You have to do it. When in doubt, make should and may shalls, and you're going to be fine. You don't have to make a decision, but it's very infrequently that we actually ignore a provision and just say it says may. We don't have to do it. By and large, we do. We equate shoulds and mays to shalls in most cases. But if you get yourself in a bind, I'll give an example in a minute. You may want to talk to the owner of the bridge and say, I think I want to violate this extra provision. Not violate, I'm going to treat it as a true may, and I'm going to ignore it. But other things, before I get to that, I want to talk about just the code is written by committees. And sometimes these committees make a mess of these provisions. And this is one of my favorite screwed up provisions. It has to do with designing pre-stress girders. You don't need to know about pre-stress. But if you read the first part of the provision, it says the factored splitting resistance of a pre-tension anchorage zone provided by reinforcement at the ends of pre-tension beams shall be taken as P sub R equals S sub S AS. You might say, well, that's a pretty simple equation. It doesn't define what P sub R is. You go on, you read it, it tells you Fs is the stress in the steel not to exceed 20 KSI. A sub S is the area reinforcement with an H over 4 at the end of the beam. H is the overall depth of precast member. So what the heck is P sub R? So I start reading the code. I go first paragraph, second paragraph, third, fourth, fifth, sixth paragraph. The resistance should not be less than 4% of the total pre-stress force of transfer. That's P sub R. It's a terribly written equation. The equation should be what I put in there. It should be 0.04 times PT, was 4% of the total pre-stress force at transfer. Has to be less than or equal to Fs over Fs times As. People screw up this equation all the time because they don't read it properly. So it's a good example of really poorly written language. So there are provisions in the AASHTO code, it is not perfect, that are difficult to read, and you just have to read them carefully. Words matter. If there's an and or an or, that means two different things in the code. In this case, they give an equation, the nominal buckling resistance shall be taken as whatever there is in the equation, but not to exceed the smaller of R sub H FYC and FYW divided by 0.7. If that was an or, it means something completely different. If it's and, it cannot exceed either one of those terms. If it's an or, it can't exceed one of the terms. There aren't many ors in the code, but you have to be careful with ands and ors. Here's another good example. They put bullet lists. They have a provision, and this is interesting. It says, we're required lateral bracing should, here's a should, be placed either in or near the plane of the flange, blah, 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 blah. And it gives, but not limited to, 3 bullets. The first bullet has a comma. The second bullet has a comma and an and. That's known as the Oxford comma. And the third bullet. So the question is, well, how do I apply this provision? The fact that it says and, all 3 of those bullets have to be satisfied to use this provision. If it was an or, then only one had to be satisfied. So be very careful how you read the code. These are the kind of things that are throughout the entire code. Commas, ands, and ors are important. Here's another example of just the most screwed up provision I could possibly find. This is in the steel design section for web load shedding factor, R sub B. When checking constructability according to provision article 610.3.2 or blah, 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 then RB shall be taken equal to otherwise, I'll point to these things. So you got a otherwise, which is the same as an or otherwise. For all the cases, for longitudinal stiffness sections, for all the cases, homogeneous longitudinal stiffening curve, blah, blah, going through this whole thing, I put down help. Oh my God, I think if I gave this equation, this provision to 10 engineers, I would get 10 completely different answers. Fortunately, we use computer software to design bridges. This is just out of control, way too complicated for most engineers. It's, in my opinion, this is a terribly written code provision. It's dead accurate. I actually know the professor who did the research on this. He's brilliant, but this is almost unworkable, this kind of thing. So I put help here. So you're going to find provisions in the AASHTO specifications that are rather difficult to follow. And that's why you have to have experience, and that's why you have to work with somebody who has experience to help you decipher some of this language. Again, back to words matter, mays and shall. I love this provision here. It says for segmental pre-stressed girders, blah, blah, blah. All right. The related losses than those specified in Article 5933 may be determined in accordance with the provisions of this article. But for precast pretension girders without blah, 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 Articles 59344 and 59345 shall be considered. I like the word it says shall be considered. Shall means it's mandatory. Considered means it's optional. Another example of a poorly written provision. Again, when in doubt, shalls are shalls, mays are shalls, you're going to be okay. This is one of my favorite may provisions that we often violate. Owners let us violate this. And this has to do optional. The title of the provision is actually optional span criteria for span depth ratios. And what this basically says is the ratio of the span length to the depth of girder should or may be, there might be a minimum thickness you can make the structure. So, and of course, you got these equations like kind of funky. It's 0.033 L. In the old days, the old code, it used to say span divided for the minimum depth of beam was span divided by 30, and the minimum depth of beam plus deck was span divided by 25. So, but it's a may, and there are cases, and especially in New Jersey, this happens, where we have to really minimize the thickness of the structure to get trucks underneath the bridge or to get water underneath a river bridge, that we sometimes violate these a little bit. We don't violate them by a lot. So if this equation says the minimum beam is 4 feet deep, but I want to make it 3 foot 10 inches, you talk to the owner. 9 times out of 10, the owner will say we're okay with going 3 feet 10. We can design it for strength. We can check it for deflection, but we're going to violate this may provision in the code by allowing it to go slightly over. This is the one provision that I know on a routine basis is overridden by designers. So to wrap things up, we're on our last slide, and I said we go a little more than an hour, and we're there. The AASHTO LRFD bridge specifications are an all-inclusive design code. It was developed and maintained by the AASHTO committee. The key thing, specification and code are the same thing, and there's a committee that maintains this document. It is a probability-based design code. It is a modern probability-based, and it's based on those beta factors with a certain probability of failure that I think it's like something 1 in 20,000 or something like that. I could be completely off on that number. I'm just going from my memory. The key thing to understand, the most common form of design for beams is a simplified line girder approach using livelihood distribution factors. We do not do 3D analysis for every bridge. We do it for special bridges. And lastly, you just need to exercise really great care in reading the provisions in the code and the specification, because words matter, and not all provisions are properly written, and there's some things are difficult to read. But experience helps, but reading things very carefully also helps a lot. When in doubt, if you see a may, treat it as a shall. If you see a should, treat it as a shall. That's my advice to you. But if you're a bridge owner, like a DOT, they look at those shalls and mays and make decisions on whether or not a may is something that is optional. But when in doubt, treat everything as a shall. I believe that's all I have. So it was what, an hour and 15 minutes? That's kind of where I wanted to fall. So any questions? I can't hear you, but I can see you clapping. Thank you.
So, thank you, Mike. Do you guys have any questions? You have to ask some questions, right? I may have one question related to HL93, right?
Yep.
Some people say the live load, the live distribution, live load, main live load distributed is a convey of trucks.
Yes.
And it, before and after and underneath the HS20, which I find it difficult to digest for a student, to convince them that there is a live load under the truck.
A live load under the truck. Okay.
Yeah, because it's a live load.
Oh, I see. You got the wheel load on top of the lane load.
Yes.
Yeah, and the answer to that is, like I said, it is a notional load. It's not you're not having 2 trucks on top of each other or a lane load, a uniform load on top of the truck. They actually looked at eliminating the live load, the uniform load under the truck, and it didn't make that much of a difference.
Okay.
But for computer programming, it's easier to have it just the whole length of the bridge. To try to have the computer program say, well, I'm going to have a uniform load in front of the truck and behind the truck and nothing under the truck.
I see.
The AASHTO committee thought that was too complicated for the programmers. So they said, no, we're just going to go live load the uniform load the whole length of the bridge and put the wheel loads on top of it. You're right. It doesn't make sense. It's like as a structural engineer, you say, I can't have a truck on top of a truck. That doesn't make any sense. Or a truck on top of a car.
Yeah.
But again, you have to understand it's a notional load. It's not a real truck. It is a loading combination that'll give you results that are consistent with what's driving down the highway. It is not a real truck. So that's my answer. And the other thing too, I have people always tell me LRFD is worse than standard specifications because we're applying twice as much live load as the standard specifications. Because in the standard specifications, it was either the truck load or the lane load. They were not applied at the same time. So people are saying like, oh, I hate LRFD because we're putting twice as much load on the bridge. But what they're forgetting to take into account is two things. One, the distribution factor has changed. Two, the load factor changed from 2.2 to 1.75. Significant drop in load factor, which brings everything back down to unity, which I showed in that plot. So we are not applying twice as much live load. We are applying essentially the same load we had before. More accurately, though.
Any questions? So if no question,
if you paid attention to this lecture, you know more than most practicing bridge engineers, because I routinely get into these discussions with practicing bridge engineers where they don't understand the code. They don't understand the live load.
Yeah, appreciate that. Thank you very much, Mike, and we'll keep in touch. Yeah.
No questions about anything. I don't care. I've been.
I was like, you guys, anything maybe
practical. 40 years. You got to have a question or two.
Okay, let's have like maybe 2-point bonus for questions.
There you go.
Yeah, just make it. Come with questions, guys.
Okay, that's okay. It's fine.
Okay, sounds good. Thank you, Mike.
Okay, it was a pleasure being here today. Thank you all. And good luck in your class. You all going to be good practicing bridge engineers when you're done. And yeah, if there's any questions after the fact, you can always send me an email.
Thank you very much. I appreciate it.
Okay.
Thank you.
Have a nice day.
Thanks, Mike.
Bye-bye.